You're listening to KTAL 101.5 low power FM in Las Cruces, New Mexico. Welcome back to this new-ish show, Science. Let's take a look. I'm your host, Vince Gutschick, and I'll be with you here for an hour from noon each Tuesday. We started off with sort of a long ramble about why plants are green and got all the way up to groundwater depletion in northern India. So that's the style here. We're going to ramble all over. The next thing I'd like to go on is risks, and particularly risks to life and health. It's the way the world works. We can distinguish risks from hazards. I saw this nicely put recently. There's raw risk, which is what's the probability of something adverse happening, and the hazard means how impactful is it. If you have a risk of a bumblebee stinging you, that's one thing. If you have a risk of a car hitting you, that's much more of an impact. Now, the other thing about risk is that it is difficult to assess. You might read sometimes that there are certain risks, like your chance of dying in an airplane crash is, say 1 in 100,000 flying hours. It's probably more than that, maybe a million. But it depends on where you're flying. The more you know about your exact situation, the more tightly you can define the risk. Your gender, your eating habits, and so on, all affect how you would actually look at a risk. So don't take these broad risk assessments too seriously until you know more about it. Okay, so there are risks that we accept voluntarily. That includes driving, taking an airplane flight. There are risks that we accept reluctantly, you might say involuntarily, but consciously, more or less. That includes having power plants operating with things they put out, including, let's say, particulates, mercury, and so on from coal-fired power plants. By the way, there was an assessment by Harvard and the Tufts School of Medicine estimating that about 30,000 Americans die a year from coal-fired power plant emissions. And it is all through the whole life cycle, but a lot of it is in the actual operation of a power plant. Some of it's in the mining and so on. Anyway, let's take something that we accept, and almost all of us have no notion that we are at risk. Bananas. Well, really, potassium. Okay, potassium is an essential nutrient for us, but it's weakly radioactive. And you may have heard that. It's gotten some amusing press. But most of this is a pretty mild threat. You can't avoid eating potassium. But about 1/100% of potassium is radioactive. It's called potassium-40. That means that its atomic weight is 40. It has 19 protons and 21 neutrons in its nucleus. Now, what can happen to that? It's pretty unique. It has 3 different ways of breaking up. One way is it can convert a neutron into a proton and an electron. The electron leaves at high energy, like in the units that physicists commonly use, about 1 million electron volts. I think it's 1.33. So that electron comes out, blasting its way through the surrounding milieu in our cells. It can ionize the other constituents of the cell. It could be water, it could be proteins or whatever. And that could end up with damage to a protein or whatever. That's not too serious. We've got lots of proteins. We can always make more. But there's also DNA, which is our continuing blueprint for how we're going to keep making proteins, how we're going to divide that cell to make replacements, and so on. And I think we've heard a lot about DNA. So that's part of what it can do. The second way that it can decay is by pulling an electron from one of the shells nearest the nucleus, the ones that are circulating outside the nucleus, the ones that participate in chemical reactions ultimately, and it converts a proton into a neutron. So now what we have is an atom that has a lower atomic number. It only has 18 protons. That's argon. And we now have argon-40. That's 1% of our total atmosphere on Earth. And it all came from the decay of potassium-40 in this second mode. And that's about 11% of the way that potassium-40 decays. It also causes an energetic gamma ray to come out, so that's damaging. And a third way, which is only like 1/100% of the time, is that it kicks out a positive electron, a positron, and that leaves one less positive charge. Again, we're making argon. When that positron, which is antimatter, hits an electron somewhere in the area, they annihilate into, you might say, pure energy, some gamma rays, again, damaging. This isn't horribly impactful, first of all, because we're not talking about a lot of radioactivity. Although you might think potassium-40 in the whole mantle of the Earth for decaying and helping heat the mantle, that keeps plate tectonics going. Okay, what do we need plate tectonics for? We don't need it for earthquakes, but that's part of it. But we do need it to renew the surface of the Earth. If you look at places that have not been renewed by plates moving, diving, reemerging, then, they don't reemerge, they're spreading ridges. Then you've got places like Australia, where some of the landscape has been unmoved for, a couple billion years, and it's very nutrient deficient. Now, plate tectonics and mantle circulation also helps provide volcanoes. Again, we don't like the eruptions, but we do like the rich soil that comes from them. So Hawaii gets some pretty nice soil, so does Indonesia, but so many eruptions. So this is a little bit off track of what potassium is doing in our bodies. What else is happening in our bodies that is a risk that we're typically totally unaware of? Well, what else can cause DNA mutations if we want to focus on something that has a high impact? There are DNA copying errors, or even transcription errors, where you go from, transcription errors from DNA to RNA and make proteins. The fidelity of copying DNA is pretty fabulous. You've got 4 bases that can determine what a section of DNA codes for. So every 3 bases in a row, properly framed, you might say, is going to say there's an amino acid that needs to be put into a protein. Well, if you change one of those bases, you may change the protein. Now, it's not guaranteed. Think of it this way. We have to put about 21 different proteins into our 21 different amino acids into our proteins. How many ways can we specify things with 3 bases, each with 4 possibilities, A, T, G, C? Well, 4 times 4 times 4, which is 64. That means that there's redundancy. There can be 2 or more different sequences of 3 bases that specify the same amino acid. So some of the changes don't make any difference immediately in the proteins that we make. Some of them do. It's not only the proteins that are made that's important, it's also what we call regulatory sequences. The biggest changes in the genome between chimpanzees and us from a common ancestor is we have more regulatory sequences that help determine how our brains develop and everything else. So it's not just proteins. Okay. Copying errors are pretty low with the DNA polymerases. There's error correcting codes, but we still get errors. And then there's some purely chemical things that can happen. One of the bases is cytosine, and if it loses an amino group by just some basic chemical reactions not involving our metabolism, it can be read as a G, a guanine, instead of a cytosine, and then we've got a mutation. So we end up with a fair number of mutations as we go along in life. Some of them just affect basic bodily function, not too badly. Some of them can eventually lead to cancer. Not very common, although as we live longer, it is becoming a pretty big risk. What else can cause mutations in DNA? Well, there are cosmic rays. You can't avoid those. Okay, they come from distant parts of the universe. What they are nuclei of atoms. It might be iron atoms or hydrogen atoms, protons, and they've been accelerated to fantastic velocities, tiny fraction away from the ultimate limit, the speed of light. When these come barreling into something like the atmosphere or us or whatever, they're going to break apart a lot of things. They're going to break apart nuclei. You end up with what's called a cosmic ray shower. And you've got all of these highly energetic particles, which can, again, do all the ionization and other things to our normal molecules in our body. And, well, it's going to be happening to us. We can't stop it. One way that we're protected is by our atmosphere. Even though it looks pretty tenuous, think of it this way. Above every square meter of land where we live, at least at sea level, there are 10,000 kilograms of air above us. That's 10 metric tons. So that's a good shield. And of course, if you're talking about cosmic rays trying to come at us from below, the Earth is very good at shielding us. You can get more cosmic rays in various ways. You can live at higher altitude. We have a few more cosmic rays impacts here at Las Cruces compared to sea level. If it's anything like air pressure, then you might say it's about 12% more. If you fly at high altitudes, then you get many more cosmic rays. So transoceanic, transcontinental pilots who do that route a lot, I think I recall that it was about 10 times what the average person gets from cosmic rays. Okay, but we've got lots of other sources. Probably the biggest voluntary source of exposure to things akin to cosmic rays, energetic radioactive particles, is smoking. Tobacco naturally contains polonium, and I think some of it comes from the radioactive, uranium in some of the phosphate deposits, say in Florida, Morocco, etc. Polonium is an emitter of alpha rays. They're basically fragments of a nucleus. 2 protons, 2 neutrons bound together. Well, that's a helium nucleus. It's an alpha ray. And they don't travel very far, but when they do travel around, they really move the other nuclei around. They knock things out. So they're potentially the most damaging radiation. So stay away from polonium. And an example of how bad polonium is, of course, the assassination by the Russians of one of the dissidents with polonium-210, which only a few nations have. Yeah, that was pretty blatant. Okay, so again, going back to what mutations do, they can make a difference in the protein or in the regulatory sequence. They can make it at just one spot in the DNA. So now we've got, say, a different protein. Maybe that makes a difference in the function, a significant difference. Maybe it doesn't. But it does. We have, I forget how many average single nucleotide polymorphisms, those single changes ourselves over our lifetime. And then there's other things that happen. You get chromosome rearrangements that change our whole genome. I recall that we have about 6 new mutations in our germline, the sperm and eggs, per generation. Again, nothing we can do about that. Sometimes it's damaging, sometimes it's controlled, and sometimes, very infrequently, it's beneficial. I'm going to take another break here, and I'll be back. You're listening to KTAL LP in Las Cruces, New Mexico, 101.5 FM on your dial or your virtual dial for most of us. And you can also stream us at lccommunityradio.org. You can also find a donate button there because this is a community service and it's supported by donations. So we'll talk to you pretty soon.